Hello and welcome to Disseminate, the podcast bringing you the latest computer science research. I'm your host, Jack Wardby. I'm delighted to say I'm joined today by Michael Abebe, who will be talking about his ACM Sigmod paper, Proteus, Autonomous Adaptive Storage for Mixed Workloads. Michael is a PhD student in the Data Systems group at the University of Waterloo. He's interested in distributed systems, databases, and machine learning. Especially, he's interested in building adaptive and distributed data systems. Michael, thanks for joining us on the show.
Happy to be here.
Can you start off by explaining to our listeners what is a mixed workload?
Yeah, that's a great question. So in databases, we typically think of workloads falling into two broad categories: transaction processing and analytical processing. So you can think of transaction processing as something like what you do when you're placing orders on Amazon, right? Adding things to your cart and then clicking purchase, and all that order information needs to be recorded in the database. Whereas analytical processing, you can think of as maybe someone at Amazon who is doing stuff like trying to analyze sales data over the past month, maybe look for trends in order history and stuff like that. So a mixed workload is when a database has both of those two types of workloads present in it. So you'd, exactly like that example I said, you'd have people submitting their orders as well as analysts running queries to try to learn information.
So what is the challenge database systems face in trying to support these mixed workloads?
Yeah, so there's several challenges. The first is that they are, these workloads often have conflicting goals, right? So you want your analytics to run quickly, and you want your transaction processing to support high throughput. And so this leads to natural conflicts in things like concurrency control and storage layouts. So in this work, we were really focused on the conflict that arises from storage layouts. So what people have found historically is that laying out your data in a row format, so storing your entire row of data contiguously before moving on to storing the next one, works really well for transactional workloads. Whereas for analytical workloads, people have found that storing data in columns works really well. So what that means would be store, say, all your order IDs in a column contiguously, and then store your users who placed those orders contiguously, and then store the price of the order, right? And so these are conflicting because when you have a workload that has both types of access patterns, it's not easy to know what layout of data that you should choose.
How have previous database systems tried to support mixed workloads? How have they tried to combine row stores and column stores, and what are the drawbacks of their previous approaches?
Yeah, so prior approaches typically fall into one of two categories. So the simplest approach is to just pick a layout and suffer poor performance on one aspect of the workload. So basically say, well, you know, we care more about transactional processing, so we'll keep it in row format, or we care more about analytical processing, so keep it in columnar format. But the kind of more traditional approach is to have two separate copies of your data, one entirely in a row format where you run your transactions, and then one in a columnar format where you run your analytical queries. And periodically you take your updates from the row format and then apply them in bulk on the columnar format. And so there's two key limitations with this approach. First is the storage overhead of doing this, right? You're storing every data item twice, so you need to, pay for your storage to actually maintain those versions, as well as, the cost of actually, managing and applying those updates on both copies of data. The second is that if you simply run your analytics on your columnar data where you're only periodically applying your updates, then you're going to be running analytics over stale or data that's missing. And so this means that you're not going to get the freshest insights in your analytics. So if we go back to that example of querying for order patterns over a month, you might be missing the last 15 minutes or last hour or last day, depending on how frequently you apply those updates.
So with these, the drawbacks of previous approaches in mind, tell us about Proteus. What are the design goals of Proteus? How do we go about getting good performance for mixed workloads? What's the magic sauce in Proteus that allows us to do this?
Yeah, so Proteus tries to do things adaptively. And what this means is that it's making decisions on the fly about how data should be stored and in what format. So what that means is that it has the choice to store data in a row format or a column format, or it can choose to replicate the data in both. And importantly, this is not a global decision. It's making this decision on a finer grained granularity of what we call a data partition. So subsets of the data. And Proteus is defining what these partitions are dynamically as well, right? And so what this allows us to do is that, it allows us to store data that's mostly used in analytical queries in a columnar format, and store data that's mostly used in transactional processing, say your most recent insertions, in a row format. And then the stuff in between, it's kind of keeping data in both formats and doing that dynamically. And what this allows us to do is to kind of take advantage of both worlds. So it allows us to use the latest query processing techniques and tricks that people have come up with over data in columnar formats. So things like applying compression and sorting that accelerates those analytical queries without having the trade-off of not having fresh results in our queries, because we also merge our analytical queries over those recently inserted rows as well. So basically, Proteus is flexibly storing data, but it's freeing the user from making that choice because it's doing it itself.
Can you elaborate a little bit more on the architecture of Proteus and how it actually makes these decisions?
Yeah, so Proteus has a two-tier architecture. So the one tier is the data sites that are responsible for storing and managing the data. And so this means storing data in the format that's prescribed to those data sites, executing the queries, managing any replication and concurrency control, and then applying updates to those data, either as transactions or changing the storage formats or layouts. Above those data sites, we have what we call an adaptive storage advisor. And this is really the brains of the system. So the adaptive storage advisor is going to receive the transactions, decide how it's going to execute them and where over those data sites. And also it's going to make decisions about how data should be stored and when to make those changes. And what's kind of interesting about our architecture is that this adaptive storage advisor also has some machine learning in it to predict what the workload's going to look like and predict what the latency of transactions are going to be under different storage layouts so that it can actually make these decisions in an autonomous way.
Awesome. So can you dig into a little bit more or describe a little bit more about how you actually predict the transaction latency? What's the mechanism behind that? You mentioned that there was some machine learning magic happening there. Can you elaborate on that, please?
Yeah, so Proteus decomposes transactions into key operators. So what this means is that if you have a transaction, say, going back to our example of ordering something off Amazon, Proteus is going to break that down into core building block operations, like making a network request, acquiring a transaction lock, waiting for any updates that it needs to ensure it observes consistent state, actually performing the insertion of the row, and then committing that data. And so each of these building block operators, we've defined to have different cost parameters. So for example, when you're doing an insertion, Proteus cares about the size of that record insertion. When you're acquiring a lock, Proteus cares about how contended that lock is going to be. And so Proteus keeps all these statistics and then predicts these costs using a few different techniques. The first is simple linear regression. The second is nonlinear regression. And the third is shallow neural networks. And so these different costs are all then combined by summing them because they're over distinct aspects of the transaction and to give a latency. And Proteus can then record these different observations. And as it's doing this, it's remembering what the layout of the data was that was accessed in those different operators and keeping a different model for each storage layout.
It feels to me that you're accumulating a lot of metadata there. There must be some overhead there. How does that affect performance?
Yeah, that's a great question. So Proteus keeps some of these statistics on a per partition basis, and they're heavily sampled. And so this is one of the reasons why Proteus models have a relatively small number of input parameters, because we don't want to keep tons and tons of history and observations. So Proteus keeps a reservoir sample, which means that it's of bounded size of observations for each of these different observations that it's using in training. And so this reservoir is updated as new observations come in. So over time, you're always keeping your predictions based on the more recent history. And the other thing that's important here is that when we're doing predictions on the critical path, we use our predictions on the cheaper models, the linear regression models, whereas when we're off the critical path, that's when we start to use the more expensive models. One thing that we didn't explore in this work was kind of offloading these models to another machine. But I think that's something that could be done to improve or reduce the performance overheads.
One question I do have on the architecture, with the adaptive storage advisor, it sounds as if it's a centralized sort of coordinator over the system. Does that impose any restrictions, or what are the limitations of that there? Does that kind of constrain our transactions per second, our throughput, or does each data site have its own adaptive storage advisor?
So we went for a centralized adaptive storage advisor, and in some experiments that didn't make it in the paper, but I do have, we found that this was able to sustain over 1 million transactions per second. So the bottleneck was not the adaptive storage advisor. The bottleneck was actually doing the transactional work at the data sites. And the core challenge with the adaptive storage advisor is keeping that metadata about where data is stored and in what layout in sync. But even though we're applying storage layout changes kind of continuously, the rate of change of those compared to the input rate of transactions is a couple orders of magnitude smaller. So we didn't see it become a limitation. But again, I think you could imagine an architecture where this adaptive storage advisor was partitioned or sharded or replicated if it became a bottleneck.
Yeah, so are we in the context of a single data center here? Can Proteus handle like geo-replication? Does that change the equation a little bit?
Yeah, so this work is done in the context of a single data center, or at the very most, a single availability zone, where the wide area network latency is relatively small. Okay. I think that there would be some serious challenges if you move to a geo-distributed, around the world setting, because of the necessity to go to the centralized adaptation advisor to make these decisions. So that's an environment where you probably would want a distributed advisor to make these decisions. But that would also obviously change some of the calculus of how you choose to execute transactions and what the overheads of replication would be.
Obviously, changing the storage layout has some implicit cost as well. How does Proteus decide whether that change is a good change or it's actually going to be a bad change? You're going to be wasting work. How does it decide that?
Yeah, so this is a great question, and I think really cuts to the heart of the work that we did here. And so Proteus basically breaks this core decision down into 3 components. The first and the simplest is, what is the upfront cost to actually perform that storage layout change? And so just like how Proteus predicts the latency of transactions, it can break down the latency of performing a layout change into similar operations that it can learn and predict. And a lot of those operations are actually shared with transactional work. And so we have lots of history that we can use in making those predictions. But once you know the upfront cost of what you're actually going to pay to make the layout change, then the other two components that Proteus uses to make its decisions are the expected benefit for transactions that are currently ongoing and those that are predicted to arrive. So Proteus basically computes the latency of transactions that would be affected by the layout change, and it compares the predicted latency under the current storage layout and the layout that will be changed. So for example, if Proteus decides to change the storage format from row to column, and the transactions that are accessing that partition are OLAP queries, then the predicted latency of those queries will go down because Proteus's cost model and learned cost model of operations like scans and joins are going to indicate that under this new layout that those operations take less time. And so Proteus will be inclined to make those layout changes. And so I said that Proteus does that for ongoing transactions and transactions that are predicted to arrive. So Proteus basically treats these the same, they just have slightly different weights as to the confidence of what those transactions will actually be.
So how does Proteus predict what the transaction is going to be?
Yeah, so there's two components here. The first is what the latency is going to be, and the second is what the transactions that are going to arrive are. So predicting latency of transactions uses those learned cost models that we had talked about before, and combines the different operators together, including changing the different models if data is stored in a different format. The second component of predicting what transactions are going to arrive uses two different sets of machine learning techniques here, but they're based on the assumption that workloads have recurring patterns, particularly analytical workloads. So for example, that query that we talked about at the beginning of what is the sales information over a month, that might be a query that's run as an hourly job or every 5 minutes as part of refreshing a dashboard. And so Proteus uses a machine learning technique known as SPAR, or sparse periodic autoregression, as well as another technique where it combines a recurrent neural network with a trend line. And so the key observation here is that periodic behavior often recurs on maybe a known or an unknown time frame, say hourly, daily, or monthly, as well as it's subject to local trends. So maybe over a month, this query runs more frequently. So by combining a periodic prediction with a trend prediction, Proteus can have some confidence about what transactions or queries are likely to arrive in the system.
So how did you evaluate Proteus? What benchmarks did you use?
Yeah, so the core of Proteus's evaluation uses the CH benchmark, and the CH benchmark combines two industry standard benchmarks, TPCC, which is a transactional workload, kind of similar to that example that I was using with ordering things on Amazon, and TPCH, which is an analytical workload. And again, sort of similar to that example of a query where you're looking for order sales history over a month. And so this is a common mixed workload that is used to evaluate such systems. And we also did some experimentation with Twitter, where we combined some of the Twitter core APIs, things like inserting tweets, looking for tweets from followers, with some of the types of queries that you can run over Twitter's Firehose API. And importantly, for Twitter, this is not over real Twitter data, it's over generated synthetic benchmark data. And we compared Proteus to an implementation of a row-only store and a column-only store, as well as two systems that fully replicate data. One is another research project known as Janus, and the other is an industrial system, TIDB.
If you had to summarize your work in one thing, what is the one key insight that a listener can take away and apply to their day-to-day life?
Wow, that's a tough question. I will say that the insight that I would take away is by automatically adapting how and where data is stored, in this case, row and column data, and being selective about this storage, you can get excellent performance on mixed workloads where you don't need to sacrifice either aspect of transactional or analytical query performance.
Fantastic. So is there plans to make Proteus publicly available? Are you going to spin this out as a new database product, or is it purely for research?
We're hoping that we can make it available going forward. Some aspects of it are still under review for another conference, so hopefully that gets in and we can make everything publicly available. No plans to commercialize it or anything like that, so hoping that this is something that the research community can build on.
What else do you have planned for? So you obviously have this other publication under review at the moment. What are the next steps?
Well, I'm wrapping up my PhD, so I'm not quite sure where exactly my research will go next, but I think that this work in particular has a few potentially really nice extensions. The first is something that we had talked about, investigating how this works in a geo-distributed environment, global at a global scale, not just within a data center or an availability zone. And the second is, how does this approach change in a disaggregated environment where storage and compute are decoupled? Again, I think that kind of changes some of the calculus of how data is stored and where it should be placed. And I think one thing that would be really interesting with that is, what could a cloud provider do when they have control of both storage and the database? And how could they use these kind of techniques to automatically change the layouts and the formats for a customer without them actually knowing it?
What was the most interesting or perhaps unexpected lesson you've learned over the course of your PhD of working with distributed databases and specifically with HTAP database systems?
Well, I think one thing that was really interesting is how much work has been done on OLAP and OLTP performance independently. So, for example, there's this really nice book that's available on the design and implementation of modern column stores, right? And it has tons of algorithms and techniques that are used to speed up OLAP queries. And I can't think of an equivalent book for OLTP off the top of my head, but many do exist. But then how little work has actually been done on the challenge of what happens when you have these mixed workloads, right? So not as much time has been spent on, well, how do these techniques apply when you're also dealing with updates to your analytical data as well. And so I think that this is really an exciting area that hasn't been examined as much, and it poses a bunch of challenges because, for example, in that book about column stores, so much of it assumes that data is read-only, which just isn't true when you have mixed workloads. So trying to apply these techniques when you have updates was a real challenge.
Do you think the best system architecture is a single system that can handle both workloads, as opposed to specialized systems connected via some sort of ETL process? Do you think the one size almost fits all approach is better?
Yeah, I think it is better because one of the things that I've come back to a lot recently is these quotes from Ed Codd, one of the original relational database people from the 80s, where he says something along the lines of, a relational database or a database in general should just allow users to tell you what to store, what data to store, and what the query that it wants to execute is, and that the system should then make those decisions of how to execute that query, how to store the result by itself. And so these separate systems, what you have to do is then you're kind of pushing that work back up to the developer, who then needs to make a decision, and it's probably an incomplete decision of, well, I got this query, where should I run it? Or, how do I know that this query is run and it's going to see the results of this other update that I made when they're in two disjoint systems? So I think systems should provide a nice unified interface that allows users to just worry about what they want to store and how they want to query it, and leave everything else to the system under the covers. And work like mine has shown that it's possible to get good performance out of such approaches.
That's fascinating. And one last question. What attracted you to work in this area?
I've been interested in distributed systems and the challenges that come from that for a long time, starting with some internships in undergrad that just really exposed me to these really challenging problems. And databases is, almost every application at some layer requires a database to interact with, and managing and storing data at scale is one of the challenges that arises from distributed systems. So to me, it's always distributed databases is a really nice intersection of challenging problems. And I think HTAP in particular is just another example of combining two things that they're challenging. So I've always found the intersections of areas to be the most interesting and challenging and unexplored. So yeah, that's what led me to distributed databases and HTAP in particular.
Brilliant. Well, I hope this podcast and this interview attracts more people to it as well. So I think we'll end it there. Thank you so much, Michael. If you are interested in knowing more about Michael's work, I'll put links to his paper in the show notes and all of the other relevant materials. And thank you for being on the show, Michael, and we'll see you next time.
Thanks for having me.